Okay, so in the last lecture, we saw backward proofs. This time we're going to see forward proofs, and that will conclude the first part of the course. So the course has 4 parts, and this is the basics, the basics of Lean. And forward proofs already explained in last lecture, how they work. So if we take this this example here, where we have these 3 hypotheses, we have this goal here. The forward way to proceed would be to follow the alphabetical order, to start at A and end at C. So you have A, and then you apply modus ponens with A implies B to obtain B. So then you derive B, and then you use B, and again you perform a modus ponens with B implies C, and then you obtain C, and C is exactly what you wanted to prove, so you've won. Victory. So that's a forward proof. And although backward proofs, the tactical proofs we saw last time, tend to be easier to find, either by computer or even by humans, forward proofs have the advantage that you can impose some structure. If you have a good understanding of what you're doing, then you might want to go forward. So in particular, mathematicians will tend to go forward for the big picture and then backwards for the small details of the proof, right? So if you have a big problem to attack, you will say, okay, first we'll do this, then we'll do that, then we'll do that. See, this is a plan. This is a forward plan, right? And then to attack the small goals that emerge along the way, then you can go backward and it becomes a video game, right? So theorem proving is very much a tension between forward and backwards, between mindful and mindless, being on automatic mode and just grinding like in a video game, or actually using your brain and creativity. And part of the art of theorem proving is to be in the right mode at the right moment, to turn on and turn off your brain at the right moment, because you don't want your brain to be on all the time, 8 hours or more a day if you do theorem proving for a living, like some people do. Okay, so these forward proofs in Lean, they take the form of so-called proof terms, or just proofs, we call them, right? So that's the default mode of Lean, actually. So when you don't write begin, end, or by, you're in proof mode in some sense, or writing a proof term. And these proof terms, you have, I like to distinguish two types of these proof terms. The structured proofs, which resemble what humans would write. And then you have the raw proof terms, which are kind of more low level and closer to the lambda calculus. But ultimately, they're more or less the same, as we will see. It's just that, one style is maybe more readable for humans, more pleasant to look at, and the other one is, more pleasant, I guess, for Lean to look at. And you can mix and match the 2 styles. There's no real distinction in Lean between structured proofs and raw proof terms. It's just a useful concept, a useful didactic concept. And I'll start with the human-oriented structured proofs. So this is this section here, the structured constructs. So the very first structured construct that we have is simply a lemma name, right? We can always use a lemma name as a proof, right? So here, you see, we prove, well, here I put a sorry, but I think we already proved it last time, commutativity of addition. So now we've proved it, and we can use it here to prove an instance of it, right? So you see here is the same lemma, except that we have 0 for m. And then we can apply the lemma, and we see the lemma has 2 arguments here. 2 parameters, I should say, because they're on the left-hand side of the column, and we can pass values for the parameters, and then it's an exact fit, right? Here, we're supposed to supply a proof of that property, and this is exactly what we've provided by, giving the name of lemma and the right arguments. And we can even, as if it were a term, we can treat it like a term, and we can say check on it, except that, okay, here I'm outside the scope, so it complains about n, so I'm going to declare n to be not, right? And now you see, it says, oh, yeah, it says the property that this proves is, the lemma that, that this is add 0. Well, wait a second. I'll try to keep it there. Oh, it's gone. Here, this part here. This is the actual lemma, and this is exactly what we're trying to prove here. So it's a perfect match. We can just put colon equal and then put, the lemma, right? So we say this lemma equals that lemma, if you like. Or another way to look at it is the proof of this equals the proof of that. And that's actually a more fruitful way of thinking about things in Lean. So this is actually not the lemma name, this is a proof name, right? That would be the lemma, but what we're actually naming here is the proof, and of course the statement that goes with it. But I'll come back to that, don't worry. Here's another proof of the same lemma. This time I enter tactic mode, then I use exec, and then I specify exactly the lemma that I want, right? So you see that by and exact are almost inverses of each other. So by enters tactic mode and exact enters term mode again, right? So if you see a by exact, then you can usually just remove it like this, but I just wanted to show it. If we try to remove the arguments, it doesn't work. If we use apply instead, it does work, because apply is smarter. It will, try to make things fit, right? So its philosophy is was nicht passt, wird passend gemacht, right? So what doesn't fit is made to fit. Okay. Is there a Dutch motto for this? I don't know. Would be nice. Okay. So far so good. This was really the basics. Just a lemma name, possibly with some arguments, is a proof, is a structured proof. What you also have is fix, assume, and show. And then this mimics what mathematicians do. So I'll just show it here with an example. I hope this is big enough. So a typical proof has this format. It starts with fix, which fixes some variables for the, for the length of the proof. And mathematicians will typically say, like, let A, B, C be arbitrary but unknown natural numbers, right? Or a shorter version of it, like fix is also a word you can use. Fix A, B, and C. You can specify the type. You can write colon, blah, 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 natural number. Usually types are fairly clear if you choose good variable names. So they're, you actually clutter the proof often by adding the types. Then you have one or several or maybe 0 assumes. Here I put just one. So those are the hypotheses, the actual formulas, F's, and you give them names like H here. We'll skip the middle of the proof, but this is where the action happens. And at the end we say show and then the goal. So we repeat the goal. And then we say from and we specify a proof. So the sorry stand for proofs. And the idea here is that we want the proofs to be explicit, like a human proof. Right, so humans will say, oh, and now we have derived blah, 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 as desired, right? So they put the emphasis, or as required. So they put the emphasis on the fact that, I mean, you repeat what you wanted to prove once you've proved it, and then you point out, hey, this is exactly what I needed to prove. Quid erat demonstrandum, right? Or quod erat demonstrandum, so QED. So this is a structure of a proof. And here, if we we go back to the to Visual Studio. Here we see first there's a fix. Unfortunately, the fix is not shown in blue because it's not a real keyword. It's just something we introduced for this course. But just pretend it's blue, like assume and show. So here you see we want to prove this property which we've seen before, and the first thing we need to do is fix the A and the B in our context, and this is done here in structured proofs using fix, just like it was done using intro in in a tactical proof. And then here we use assume for the two properties, but again that would have been an intro in a tactical proof, right? So there's some correspondence between the two here. And here in the middle, this is where we could have arbitrary reasoning, but in this case, the reasoning is so simple that we can do it directly here, directly in the show. So then the show has a very strange syntax. It's show you repeat the statement of the goal, comma, from, and then you put the proof. I like to put the proof on a separate line, but you don't have to. And this is it. This is the format, but you have to put the comma and you have to put the from and so on. It's a very strange syntax, but just take it as a whole. So a show has this form. Actually, there are alternative syntaxes to show, but they only make things even more confusing. So just always write it like this, and things should be okay, right? And then at the very end, you need a proof for show, and it's provided here. And in this case, the proof is trivial. You just provide the name of a lemma, or actually an assumption, right? Because we have this assumption A, and we need to show A, so it's a perfect match. We just use it, right? If we tried something else, it wouldn't work. And what is nice with the proof mode is you can also put an underscore, and it will tell you, it shows you the goal, right? So this would be in tactic mode here. So it tells you, with these assumptions, you have to prove that. So you see everything that's in your context in case you have trouble seeing it textually here in your lemma. Here's another example. The syntax here is very strange, right? Well, I mean, this is not idiomatic. This is not how we would write this proof, but we can also write begin, we can write exact, we can write end, right? So inside the from, we can enter tactic mode, and then we can use exact again to enter term mode again. But typically what we would do is simply put all of these things as parameters here on the left-hand side of the column, and then we don't have to fix and assume them. They're already parameters of the lemma, and then we just need to specify HA, and we've won. So that's the absolute simplest way of writing that proof, if we can. So now I said that in the middle of a structured proof, you can have arbitrary reasoning, and it's not a pun. We can have basically. So mathematicians would say something like, oh, and therefore we have blah blah blah, and hence we have blah blah blah, and therefore we have, and we obtain, and and so on. So it's this have is used a lot for intermediate steps in English language proofs, and it's the same in Lean as well. So it has a bit the same syntax as assume, but then it has a colon equal, and then you have to provide a proof. And again, I like to put my proofs in the following line and to indent them so that they don't interfere with the big picture of the proof. You see, when I look at this proof, I see immediately, okay, it has 1, 2, 3, 4 steps, and then I can fade out the proofs, because the proofs are not so important typically. You want to see the big picture first. Because if you start doing this, then you see that it has 4 steps, but you have problems seeing the formulas, right? The B here, which is very important, the C here, and the A are hidden, in so many symbols. So I recommend of course, the style that is used systematically in the lecture. But you can do what you want. I'm not going to complain in exercises or homeworks if you prefer a different style, as long as it's moderately readable. And yeah, so this is our friend. This one is quite nice. It's our friend. Let's see. It's almost this one here, which I show all the time, but it's the variant where the A is part of the goal when you start. So you have A implies C when you start. So this is an A, by the way. It doesn't look like it. This is what we have to prove, and then the first thing we say is like, well, assume A. Right, so that it's in the context, and then the goal becomes C. So the show at the end is C. So typically when you develop such a proof, you would start with the frame. You would say assume A, show C, and you'd have no A's in between, and you'd have sorries, right? So something like this. You would just write this, right? And you see this proof compiles, which is a good starting point. And as I explained with terms, it's a good idea to start with terms that compile, make small changes, and try to keep them compiling. It's the same with tactical proofs, and it's the same especially with structured proofs, right? So now let's try to find the undo key, right? So here we started with A, and then we want to have B, and here, well, we have A implies B, and this is where the magic happens. Modus ponens in lean is simply juxtaposition, right? So if you have A implies B and you have A, then you just pass A to A implies B and you obtain B, right? That's you know, that's all there is to it. That's modus ponens. A implies B, A, pass it, right? So you can imagine the A here goes into the left-hand side of the arrow here, and it cancels it, and then you're left with the B, right? And then do exactly the same thing here, right? So you have B implies C, B, and then you obtain C, right? And then at the end, well, here you need to show C, but you already have C, so, right, you're done. And actually, I could, if I wanted, optimize this proof, right? I could simply put that proof directly here, and then I don't need the intermediate step. And then, well, I could continue. This is HB, right? So I could take that proof here and replace it, and then get rid of that intermediate step. And then I end up exactly with this proof here, right? So it's up to you to decide how many intermediate steps you want to have explicitly and how many you want to squeeze on one line. And of course, the more use you'll get with lean, probably the more you'll squeeze things on one line. Just like in programming, you're probably at the stage where your lines are very long and you need to break them, you know, instead of declaring lots of new variables all the time to store intermediate results. So that's really a matter of style. I'm also not going to bug you with that too much in, when grading the homework. Okay. All right.